All right, so we've learned about predicates and names. So now we're going to introduce the idea of a variable and then the idea of a quantifier, talk about existential and universal quantifiers, and then we'll reflect briefly at the end on what a quantifier really is. So variables. Well, you probably know about variables already from math. So you can probably solve an equation like this, 3x plus 7 equals 22. Solve for x is something that just about any high school student learns to do. So what makes something a variable in math? Well, what we mean when we call something a variable in math is that the variable x can take on any value at all. So here x is 5. If you solve for x, you'll get 5. But in a different equation, it can mean something completely different. So it turns out that math is not the only language that uses variables. In fact, all natural languages that contain pronouns do. So in English, the variables we call pronouns are words like I, you, he, she, it, we, you, they, someone, and something. So just like in math, pronouns are not names of particular things, but they can refer to any object depending on the sentence they're being used in. So predicate logic will introduce variables, and we use the letters x, y, and z typically, just like in math. So this constrains our language a little bit. These lowercase letters toward the end of the alphabet end up being variables, whereas the ones prior to that can still be used as names. We'll talk a little bit more about that later. So how does that work? Well, you already know that a sentence like Benito is clever can be represented as capital C, little b in predicate logic. But how would you say that someone or something is clever? Well, you might guess that it would be something like this. Capital C, x. We've introduced this idea of a variable, so why can't it be, why wouldn't it just be x is clever? That sounds like that sounds like what it would mean to say something is clever, and that's actually not right, but it's thinking right. So the problem with just letting cx mean x is clever is that it's ambiguous. We don't know whether it's saying that something is clever or that everything is clever. It could mean either one of those things. So that's why we need the idea of a quantifier. We need to be able to distinguish between statements that say some one thing is clever, or at least something is clever, or at least one thing is clever, or if we're making a much more categorical statement that everything is clever. So let's talk about the existential quantifier first. The existential quantifier is written like this. It's a backwards capital E. Now, quantifiers never occur by themselves. They always occur with predicates and variables. So we never just write the backwards E. That'll never be a well-formed formula. So in predicate logic, if we want to use the existential quantifier to write that something is clever, it'll look like this. Now, this literally says, the way to read this in English, and you want to get used to this, is there exists an x such that x is clever. Okay? So there exists an x such that x is clever. Okay? Now, The universal quantifier allows us to say things like everything is clever, and it's written as an upside down A. So we've got a backwards E and an upside down A. So in predicate logic, the proper way to write everything is clever is this. For all y, see y. Okay, so how do you read that? The proper way to read this is for all y, y is clever. So for all y, y is clever. Now you might be wondering why did I use y here? Because in the previous case with the existential quantifier I used x. So is there something important about that? The answer is no, there's nothing important about it at all. I just introduced y because I could, and to show you that variables you can choose arbitrarily between the variables you use. They don't mean anything. They don't have any intrinsic meaning, so the variables you use just don't matter. Typically, when we're writing these things, we'll use x first, and then y if we need to distinguish y from x, and then z if we need to distinguish x from y. Okay, so just to repeat, quantifiers and variables always occur together, never separately. What we say is that quantifiers bind the variables. And so a way of sort of partially stating the above point is that we can not have unbound variables in a formula. We can't have variables just floating around that aren't being bound, that aren't associated with specific quantifiers. So all of these are not woofs for one reason or another. So fx and ga, the problem here is there's no quantifier binding the x, right? Gay, again, no good. There's no quantifier binding the y. Now, here exists an x such that fx and ga or fy, x is in fact being bound by the existential quantifier. When we draw the parentheses here, everything within the parentheses is within what we say within the scope of the quantifier, and so x is there and it's being bound. But y is outside the parentheses, and anyway there is no quantifier with a y in it. So the problem here is f of y has no quantifier. Y has no quantifier binding it. Here we have for all x, but there's no x in the equation. There's only a y, and the x, the for all x, can't bind the variable y. For all x can only bind x's, not y's. Here we have this part of the formula. So there exists an x fx, then for all y fb. This part of the formula is just fine. There exists an x fx, but here the problem is that there is no y, right? So for all y f b, b is a name, not a variable, so you would need a y here to make that a woof. So we're just getting a feel for this right now. Later on we'll be very precise about the formation rules, and we'll really practice on how we construct woofs in the predicate logic. Okay, so let's talk about categorical propositions. Now, having introduced quantifiers, we're now able to use predicate logic to represent some basic kinds of categorical propositions. So there are four basic types of categorical propositions, which are covered in the chapter that we skipped. They're traditionally given names, A, E, I, and O. So here's an example of each. So an example of an A categorical proposition is all frogs are green. So all X's are Y's. We'll just use frogs and green as the predicates here. So all frogs are green. E is no frogs are green. I is some frogs are green. And O is some frogs are not green. So let's go ahead and see how each of these translates into predicate logic. Okay, so propositions of the form all X are Y, like all frogs are green, which we call A-type propositions, are typically translated with the universal quantifier as conditional propositions. So all frogs are green means, in English, if something is a frog, then it is green. So in predicate logic, we write this as for all X, if X is a frog, then X is green. That's exactly how we read that statement. For all X, if X is a frog, then X is green. Now you'll notice that in this expression, both of the X's that occur within the parentheses, here and here, are bound by the universal quantifier. So both of them. There's no limit on the number of variables. They all have to be X's in this case that can be bound by a quantifier. So we use, as it turns out, we use the parentheses to determine the scope of the quantifier. All of these two variables are within the scope of this quantifier because the quantifier is outside the parentheses, directly outside the parentheses in which they occur. Okay, so notice as well that our translation does not say all green things are frogs, right? There's a big difference between saying all frogs are green and all green things are frogs. To represent that proposition, all green things are frogs, we'd have to change the order, right? So for all X, if X is green, then it's a frog. So the order is very important. So you might wonder whether this is the only way to translate A-type categorical propositions, and the answer to that is no. As you might expect, there's actually an infinite number of ways to do this because we could just pile on double negations and ultimately use the double negation rule to demonstrate that these are logically equivalent. But that's not interesting. What is interesting is that we can use the existential quantifier to do this as well. So how would we say all frogs are green using the existential quantifier? Well, the answer is that we would introduce negation judiciously, and we would change the conditional to an ampersand, to an and. So this says, it's not the case that there exists an X such that X is a frog and it's not green, right? So all frogs are green means there are no frogs that are not green, which is what this says. It's not the case that there exists an X such that it's a frog and it's not green. In other words, all frogs are green. Now, E-type propositions, rather than saying all frogs are green, say no frogs are green. And again, we translate this typically using a universal quantifier and a conditional, but we introduce a negation. So no frogs are green is represented as for all X, if X is a frog, then it's not green. Now, just as before, the order matters. So this is not saying no green things are frogs. It's saying no frogs are green. For all X, if it's a frog, then it's not green. But it also can be translated using the existential quantifier, and you might be able to figure this one out on your own, so you might want to pause and see if you can do it. Proper way to use the existential quantifier here, again, is to use an ampersand and a negation, but now we'll say it's not the case that there exists an X such that it's a frog and it's green, okay? So nothing that's a frog is green. No frogs are green is how we would say that. Of course, that's false, but that doesn't matter. Okay, so how do we say some frogs are green? Well, if you're thinking, you probably are thinking that I bet we use the existential quantifier here, and you're right. Propositions of the form some x or y are typically translated as conjunctions using the existential quantifier. So some frogs are green is translated as there exists an x such that x is a frog and it's green. This is kind of an interesting thing to think about. Some frogs are green is interpreted as meaning there are frogs in the world. This can't be true. Some frogs are green can't be true if there literally are no frogs. That's a big difference between the existential quantifier and the universal quantifier. If I say all frogs are green, that means if something is a frog, then it's green. And if I use the conditional if, right, something is a frog, then it's green, that doesn't mean there are any frogs at all. It just means that if something qualifies as a frog, then it's green. So big difference between the universal and the existential. We sometimes say the existential quantifier has existential import. It implies the existence of something, whereas the universal quantifier does not. Now, the universal quantifier can be used to translate this kind of statement, though. And it's analogous. You're going to introduce a negation, okay? And you will also use a conditional statement. So there exists an X, or put it this way, some frogs are green, using the universal quantifier says it's not the case that for all X, if it's a frog, then it's not green. So it's not true that if something's a frog, it's not green. In other words, some frogs really are green. So these two are logically equivalent statements. And then finally, O, some frogs are not green. So again, we'll use the existential quantifier, and again, stop and see if you can do this yourself. It's not too tricky given everything that's gone before it. We translate some frogs are not green as there is something, there exists an X, such that X is a frog and it's not green. And unsurprisingly, again, we can translate this using the universal quantifier, so give that a shot. It's going to be very similar to the previous one, except this negation is going to disappear. We'll introduce the universal quantifier and a conditional. So some frogs are not green means that it's not the case that for all X, if X is a frog, then it's green. So some frogs are not green. It's not the case that for all X, if something is a frog, then it's green. In other words, some frogs are not green. Now, one of the most common translation errors that beginning logic students make involves the I and the O type propositions. So I want to call this to your attention and see if I can help you to avoid it. People often mistakenly translate a proposition like some frogs are green as there exists an X such that if X is a frog, then X is green. So what they do, essentially, what you know is that this is wrong. We don't use the conditional. We use the ampersand, right? So what's the difference between these two? First of all, there's nothing wrong with this formula in the sense that it is a perfectly well-formed formula. In other words, the conditional statement is a meaningful statement in predicate logic. But it's just not what we mean when we say that some frogs are green. So this literally says there exists something, there exists an X, such that if it's a frog, then it is green. It does not say there exists an X such that it's a frog and it's green. All right, so there's different ways to understand why that translation with the conditional is not correct. Now, one way is to observe that a statement like some frogs are green does not tell us that we can infer from the fact that some existing thing is a frog that it's green. It just tells us that there is at least one green frog. Another way of understanding it is this. Some frogs are green can only be true if there is at least one frog. You'll remember earlier I said that when we make a statement like some frogs are green, we involve the existential quantifier because this really commits us to the existence of a frog. So some frogs are green can only be true if there is a frog somewhere and also that it's green. But a statement like there exists something such that if it is a frog, then it is green, just does not imply the existence of frogs at all, right? So again, if I were just to write it here, there exists an X such that if X is a frog, then X is green. This conditional doesn't commit us to the existence of any frogs at all. So it doesn't preserve the idea that some frog has to exist when we say some frogs are green. It really just tells us that there is something such that is either not a frog or it is green. Now, why do I say that? Well, you can really understand this from propositional logic, right? This is a logically equivalent expression. There exists an X such that either it's not a frog or it's green. Now, why is that? Well, these are logically equivalent expressions because a conditional, you'll remember from propositional logic through the rule of material implication, MI, is identical to a disjunction with the first disjunct negated, right? So if you understand that these are logically equivalent expressions, this just tells us that there's something such that it's either not a frog or it's green, which is why we're not committed to the existence of frogs at all. So there's a little bit of a long-winded explanation for why this translation is not correct, but you need to pay attention to it because there's so many ways to do this and therefore to do it incorrectly. So the best way really to avoid this mistake while translating English sentences, and we'll do a fair amount of this, is to be very leery about associating non-negated quantifiers with conditionals. So basically what I mean by this is anytime you feel you see yourself writing something of this form, there exists an X such that blank conditional blank, where you are inherently associating the existential with the conditional. Ask yourself, is that really what that English statement means? Because there are very, very few times when we actually talk like this or state a proposition that's really intended to convey this rather odd notion. All right, so this table here summarizes everything we've talked about. you've got the four categorical propositions and sort of the standard ways of translating them right here. And then you've got the alternative translations on the other side, which involve using the alternative quantifier and the judicious use of negations. Now, at the very beginning of the lecture, you'll remember we talked about these simpler statements like everything is a frog or something is a frog. We didn't mention that these two have logically equivalent expressions. So if you'll notice, everything is a frog for all x, f of x. That means it's not the case that there's something that's not a frog. Everything is a frog? Oh, well, it is not the case that there exists something that's not a frog. Alternatively, something is a frog tells us it's not the case that for all x, that everything, it's not the case that for all x, it's not a frog, right? It's not the case that everything is not a frog. Something is in fact a frog. So these are logically equivalent expressions as well. Now, if you pay real close attention, if you look at the relationship between these two and these two, it might actually start to look kind of weirdly familiar, okay? Notice what would happen. Suppose you took this negation, right? Suppose you took this negation right here, and you were somehow, for some reason, allowed to just like move it in here. So now this is double negated. So now it said, right, not fx. If the existential was, as a result of this, converted to the universal, you'd get this statement right here. And similarly with the universal quantity, if we move the negation in, so this said not, and converted this to the existential, you'd get this statement here, as long as you applied, of course, double negation. You all know that a double negated proposition is equivalent to the non-negated proposition. So if you think about that, it just might start to feel a little familiar. What is the familiarity? Let's finish by explaining that. So what are quantifiers? Well, the answer is that they are special kinds of operators, like and or, and if then, and not, and if and only if, right? They're special kinds of operators. Now, one way to see what they do is to imagine a universe with only three objects in it, okay? So say A, B, and C. So here's our little universe over here with three objects in it. Now, suppose we wanted to say about this universe that all of the objects are green. Every single one is green. So A is green, right? B is green, and C is green. Whoops. And C is green, right? So that suggests there'd be a very simple way of saying that. We can just write A is green and B is green and C is green, right? Notice we're using the conjunction. That's how we would say that. Suppose it was four objects, then we'd say D, E, F. We just keep adding the conjunctions. As you can tell, that would get pretty irritating, boring after a while. And if we were talking about infinitely large universes, it would actually become impossible because we can't write an infinitely long proposition. Do we ever talk about infinitely large universes? Well, we absolutely do. Think about math, right? There's an infinite number of numbers. If I say, for example, that every even number is divisible by 2, that's a statement about all even numbers, and there's an infinite number of even numbers. So if I was going to write that down, with conjunctions, I'd have to say 2 is divisible by 2, 4 is divisible by 2, 6 is divisible by 2, etc., etc. And it would go on for actually ever. So the alternative way of saying this, of course, is just to use the universal quantifier. For all x, g of x, everything is green. In just one little expression, we can express a long conjunction, even an infinitely long conjunction, in a very, very compact way. And so that's the beauty of the term all in English and the universal quantifier in predicate logic. All right, so what do you think the existential quantifier is? Well, once again, suppose we had a universe with only 3 objects in it, and we wanted to say that at least one of the objects in the 3-object world is round. So we change the property to round. Now, how would we say this? Well, notice that we can't, as before, just sort of put R by one of them, because that would actually pick out the one that's round, and we don't know which one. We don't know if it's A, B, or C. So we want to just say, we don't know which one is round, but one of them is round. How would we do that? Well, I bet you can figure that out. That the answer is that we would just use a disjunction. So we'd say, hey, A is round, or B is round, or C is round. We don't know which. All right? Now, the other way to say that is there exists an x such that x is round. So in an exactly analogous way, the existential quantifier is this beautifully compact way of characterizing disjunctions. So the universal quantifier is to conjunctions as the existential quantifier is to disjunctions. And that is why those lines on the previous table might have looked so familiar. Because really what we're looking at is the quantifier version of the DeMorgan's equivalence, right? Remember, the DeMorgan's applies to and or, and involves redistributing the negations in an exactly analogous way. And so these equivalences are actually going to turn out to be just as powerful in predicate logic as the DeMorgan's rules are in propositional logic. Now finally, we can translate now the argument we began with in the previous lecture into predicate logic. Remember, it was all birds have wings, some birds can't fly, some winged things can't fly. I bet you can do this now on your own. You might want to pause and give it a shot. This is a translation. For all x, if x is a bird, then x has wings. There exists an x such that x is a bird and it can't fly. Therefore, there exists an x such that x has wings and it can't fly. Now, we're not in a position to prove this argument is valid yet. That's going to be a little later after we introduce the predicate calculus, but at least we can formulate it. All right, so let's go ahead and finish with some study questions. So I'm going to give you a bunch of English expressions to translate into predicate logic, and you'll use this interpretation key here. So T equals tricky, or it means trickier than, depending on the context. D equals dangerous or more dangerous than. S equals simple or simpler than. F equals faithful or more faithful than. And we have 3 names, Alvin, Beatrice, and Karen. Notice that sometimes, but not always, I'll give you some alternative translations, but try to produce the most natural one.